Hi everyone, welcome to the course. Today we'll be talking about the first step of the AI lifecycle, which is the initiation of the machine learning model. Um, Spoiler alert, we won't do a lot of machine learning today, but we'll talk a lot about data and how to pre-process it. But hopefully, by the end of this lecture, you will understand why this is of utmost importance. So if we look at the organizational story of our overall course, last time we covered the fundamentals. What are the terms? What do they mean? AI, machine learning. What's my view on the terminology out there? And what are the relations of the terms? So I think by now, I hope you have a good understanding for that so that we can now dive into the AI lifecycle. And again, today will be about this first step, which will be a requirement for the next step, which is then about the modeling of the machine learning models and especially on how to evaluate them. But let's first start with the initiation and the objectives. I try at every beginning of every lecture to give you an idea on what's important to me and what I want you to get out of this lecture, which is classified into these four areas of exploring, understanding, intensifying, and applying. So first of all, I want you to explore the importance of defining the related problem or business problem. But in general, everything that we're trying to solve with machine learning in specific and AI in general relates to some problem in the real world. As we have this economic spin on AI, this is often a business problem, but you can even scratch the business and just talk about the real world problem. And that's something that also in my past experience is oftentimes not focused enough on. So taking your time to define the actual problem that you're trying to solve. So first thing. Second, I want you to understand the options that you have when it's about pre-processing data to make it later digestible by the algorithm, which deals a lot with different pre-processing methods, but also engineering your own features to build a good as possible data set that your models can work on. Third, I want you to intensify your knowledge about the various types of data. This is something you might have heard before if you're a little bit into computer science and potentially software engineering. So we might have a short refresher on that, or if it's your first time with these topics, at least you get a neat overview. And then finally, I want you to be able to apply those insights into gathering your own data or working with data sets that are publicly available. And this also determines the remaining agenda, right? I'll give you a short introduction, which deals with different data sources. We'll talk about the problem statement, the data gathering, sampling, data distribution, data quality, different options of data preprocessing, and then finally feature engineering. So let's dive in and have a look at what is model initiation. First of all, the important thing that you have to do is, if you want to build a machine learning model, you need data for that. Bad news, right? You want to go into the fancy stuff immediately, but no, first you have to deal with data. So the first step typically is to select relevant data from a data source, which could mean you collect that data yourself or there's a data set available. Anyhow, this looks like rather a grumpy process step, but what we do this for is we want to prepare the data to be digestible by algorithms. And that's where the fun begins, because once we did all that, our algorithms can work with it. However, our algorithms only work with specific types of problems and specific data. So we need this step of selecting the relevant data and then preparing it to be digestible by the algorithms. And one thing we always have to keep in mind is, again, we want to solve the initial business problem, right? We don't do machine learning for the sake of itself, but we want to do it to solve some kind of real world problem. So now you might ask, wait, what kind of data is he talking about and what kind of algorithms? So let me give you a short introduction. I want to give you a very, very simple example of supervised machine learning. Again, as a reminder, that's what we will be doing in the majority of this course. Nonetheless, we'll cover some other topics as well. But I want to give you a quick example. And this is by no means rocket science. It's easy to understand. What we want to end up with by the end of the model initiation step, so more or less by the end of this very lecture, is a table that looks something like that. And in machine learning terms, we have our own terms, obviously, for how this table is structured. So what you can see here as the columns, these are called the features. And what you can see here in the rows, these are called our observations. And each of these observations do have an ID. So when I talk about features and observations, I mean columns and rows in the logic of a traditional table. And that's a neat table, right? That's something that we want to end up with. Once we're there, we can give it to the algorithm. Now, what will the algorithm do here, and what is this entire step for? In supervised machine learning, if you recall the examples from the last lecture, it's always about predicting a certain class, right? We talked about the analogy of a child determining whether the car is an SUV or a sports car. It's very similar here. So as an example, I naturally, as a professor, picked students. So students, potentially students as part of this course, will attend lectures, they will submit exercises, and I might know a bunch of different characteristics or features in their language about these IDs, about these students. That's what I try to visualize right here, right? So we have a bunch of more features, anything you can imagine. I don't know, the age, the previous history of other courses, things like that. And now we know from historic data who of these students passed an exam. And this is a so-called binary classification, right? So it's true or false, 1 or 0, yes or no in this logic. So we know who of these students passed the exam. This feature, this column that we call exam pass over here, is what we call a target. That's the one that we want to predict. Coming back to the example that we had earlier of the toy cars, that would be the type of car. So SUV or sports car, over here in the logic of our table, of our data set, it's whether or not a student passed the test. And all the other features is what we call an input. And if you recall the definition of supervised learning, it's always about a mapping from an input to a target. Now, if we apply an algorithm to this data set and we tell the algorithm what our target is, right? Say this last column is our target, all the other columns are our features. The model will learn the relationships from an input to a target variable on historical data, right? We don't have to tell the model or the algorithm where to look. It will simply identify the patterns itself. We tell it, hey, these are our observations. That's our target over here. And then we have the input, the features over there. Now, where it gets interesting is, why do we do that? We call that we want to solve an initial business problem. Now, let's say we're building a model here which should predict whether or not a future student, one who has not written yet the exam, will pass it. So potentially we could intervene and say, okay, well, we should give him or her more courses or more tutors, right? Again, just a running example. But what will happen now is our model generated knowledge by having a lot of observations, and you can see only 4 here, but in reality in supervised machine learning, you need a lot of these observations, right? That's really important. Oh, by the way, one important thing is that the amount of observations over here, that's what we call n, so small n, and the amount of features that we have over here is called p. And a very good rule for building working supervised machine learning models is that our n should always be way larger than our p, so way more observations than features for that to work. Now, we have a new student, this new one over here. We know how many lectures he or she attended, how many exercises were submitted, but we don't know yet if he or she, in fact, passed the exam. The exam is in 2 weeks, right? Now, what the model did is it learned the mapping from the input to the target, identified the patterns there, and now we can apply this knowledge to instances with an unknown target variable. So in this case, it will predict, based on its knowledge, whether or not this student will pass the exam, right? And that's the entire magic. that's why we need this structured data set, so we can then build supervised machine learning models that can do exactly what I just described. And these models have to be trained. I showed you an example, how it will go through different observations in accordance with the features and then identify patterns. And these models will also need to be tested and then finally deployed, right? These are the two steps of estimating the performance by combining model training and testing, and then in the end, training a final model that is deployed in the real world within an autonomous agent where the model can make continuous predictions. But today it's not about these steps 2 and 3, but it's about the first step, about setting the foundations, including the data set characteristics. And this initiation step consists of various components. You can have a short look at it over here, but it's also the remaining agenda of today, right? It's about the problem statement, the way that you gather data, the way that you sample data, the data distribution that you have at hand, the quality of the data, the different data pre-processing methods that you can and should apply, as well as the feature engineering and vectorizing. So there are a bunch of questions that are important to answer here. And one way to depict that is this simplified process of the initiation. I do have to say, though, that it's an iterative process. So it looks very linear here. In reality, it's not. We start with gathering the data. So we need to get data from somewhere. We'll get to that in a second. We can potentially then sample it. Let's say we have too much data or too diverse data, which we potentially don't want. But then you come into this feedback loop between having a good understanding of what the data is like, so having a descriptive analysis of it on understanding what the data distribution is, because this has implications later for choosing the right performance metrics and also for selecting the right algorithms, as well as getting an understanding for the quality that you have in the data, always with regard to your business problem. And on the other hand, you engineer this data set that I just showed you, this table, all the time with data pre-processing methods and feature engineering. And while of course first you need to have a descriptive understanding of the data, the next step is then to generate this table. But in reality, this happens at the same time. You get a better understanding for the data, then you engineer your data set, and it goes back and forth. And now we want to get into these different steps in this initiation process. And let's start with the problem statement here. And just in time for the problem statement, the microphone is also working again, so hopefully you can now hear me better. Okay, so what is the problem statement about? The problem statement is what we consider a well-defined problem, and this well-defined problem has two aspects to it. The first one is the objective. So we want to describe the primary objective as well as questions that are related, that might be relevant, that help us understand this objective. So to give you an example from the financial area, right? So let's say you're a bank and the primary business goal is you want to keep current customers by predicting who is prone to move to a competitor. And related questions might be, does the channel used affect whether customers stay or go? So whether I call them, I send them an email, I hit them up on WhatsApp. Or a different question might be, will lower ATM fees significantly reduce the number of high-value customers who leave? And these are important questions because it's important to understand what is your treatment space that you have at hand, and also what is your precise question related to. And it's really important to think about that. And that's something that's typically hard to do from the outside. So there were many cases where I was working in different industries. And of course, I'm no expert in these industries. That's why I have to team up with domain experts to understand what their main objective is. Why do they want to use AI in general and machine learning in specific in the first place, right? What problem are they trying to solve? Are they simply utilizing AI because it's a hype term and apparently everyone does it right now? Or is there a significant problem, business problem, that can and should be solved with the technologies that we have at hand? And so the first step is defining the objective. And the second one is almost as important, if not even more important, is define what the success criteria are. So when would that project be successful? When would you deem this to be a successful AI implementation. And it's important to be as specific and measurable as possible, right? So if it's about churn rates, to pick the example from earlier, right? To what degree do we want to detect these moves to competitors, right? What would be successful? Also, or potentially in determining the actions that we can perform. So this combination is of immense importance, and I cannot overstress that from my own experience how important it is to spend time on that. And those questions are not related to any capabilities in data science or AI or technology or software engineering. They are related to very basic concepts in human-centric design, in understanding how you can make life better for your customer, for your partner, whoever you're working with here. And I can't overstress that. And that's where methods like design thinking come into space. Anything that is design oriented. And you might say, wait, this is no lecture about design thinking or human-centric methods. It's not. But to me, in my experience, whether or not a project is successful hugely depends on that step. If we have an adequate understanding of the precise business problem, its objective, and when it's going to be successful. Because what we'll do next is we'll translate this business problem, so the objectives and the success criteria that describe it, from a rather subjective business-oriented view into a precise machine learning problem. And once we do this step, things that might have been subjective or fuzzy before need to become clear and measurable. And one of the main choices that you have to do here as the data engineer or potentially AI engineer later then is, what kind of machine learning problem is that? And again, you can pick from supervised machine learning, unsupervised machine learning, reinforcement learning, other steps in between those, right? That I showed you 3 different examples. There are also things like semi-supervised learning, which we'll get into later. But first of all, pick like the general class of machine learning problem that you have. And let's assume it's supervised, because in most cases it's going to be supervised. What choices do you have? And there we distinguish between the classification and the regression. And for classification, it's about classifying instances into classes, like we had before, sports cars and SUVs, like we had earlier with students passing the test or not passing the test, right? So you have distinct classes that you think about, and also that your model will think in when it comes to defining the target. So the target is 1, 2, multiple classes. The other approach that you can do is regression. So having a precise numeric variable. To go back to the example that we had earlier of the students, instead of picking passing exam or not, we could have also used the precise grade between 1 and 6, for example, even up to the decimal point if we want to. And that's what a linear regression is about, predicting numerics as close as possible. Now, in this translation from the business problem to the machine learning problem, you have to make that call. You have to understand, is that best modeled by a classification task, or is that best modeled by a regression task? And I want to give you an insight from research and industry, a possible one that might be of interest here. So 2 rather recent examples show where you have to really think about the problem statement in the field that you're trying to solve. Because as this Nature news article shows, the image generation of AI often gives racist and sexist results, obviously, as you can see from these very, very graphics. And then the question is, of course, what is the initial problem that you are trying to solve with your AI image generator? And when are you successful? So are these solutions that are currently in place, have they been deemed as being successful as solving the problem when they have, in fact, these flaws? So it's important, again, to think into what is it that I'm looking at here, and what do I want to get out of these solutions, and how much could potential biases harm the solution that I'm interested in. So maybe people utilizing these generators should have asked,
wait, maybe the race and the gender are important for us. We want to have that on equal scale, or we have certain success criteria determining when these AI generators work for us, because apparently in many cases they are flawed in that regard. But not only image generators, but also if you look into the political biases of tools like ChatGPT, there's ample work showing that there is in fact a bias. So that's why it's so important to understand what are the success criteria for your model, and what are all the considerations and additional questions that you have to ask when you're aiming for building a model. Okay, so let's say we did a good job at understanding our domain and understanding the related problem. Now the next step that we want to do is gather data, because without data we can't do anything. And for that we consider various forms of data structures. The first one is structured data. Simple, standardized, very efficient, similar to what you just saw in this table. These are typically stored in a relational database, in a table with rows and columns. And if it's in a database, then typically it's accessed by these relational keys, these identifiers, which are fixed and the predefined structure. So if you've done a little bit with databases, best example here are SQL databases. These are like the holy grail in data engineering and then later in machine learning, because we can work really, really well with these structured data, like you can see in the example over here. This doesn't happen very, very often. So just so that you're aware of it, I think around 5% of data are in this format. The next level is semi-structured data. So it has kind of a self-describing structure with some organizational properties like HTML, for example, CSV, other XML databases, as you can see up there. So it does follow a predefined order, but it really lacks the formal structure that you would have in a relational database with these clear columns and these clear rows. But it can still help you. And then and by the way, a bunch of algorithms could work with that. The worst case, however, is unstructured data. The worst case in terms of machine learning, right? Because this means it needs the most work in pre-processing and then generating the features. And this represents over 80% of all data, and it's really hard to analyze, right? Machines can't work with text. Text is unstructured. So anything that's in an email on a web page needs to be somehow translated. It gets even worse with images, video, audio, right? The more we move away from numeric values, the harder it becomes, right? And so if 80% of the data in the real world is unstructured, of course we need methods to transform them into semi-structured or better structured data so the algorithms can work on it. So it is often necessary to combine different data sources and types of data and then create your data set out of that. It's especially important that the collection must be rigorous. In many cases, you as a researcher or as a practitioner will be the one collecting the data, for example, from the processes in your company, or research data from the field. So you really need to make sure that it's complete and without any gaps concerning the object of interest, right? So, for example, if you want to analyze COVID cases across the past 5 years, it's really important to have an entire time series that covers all the important points and is not missing any values in between. And we'll get into that in a second, because if you look at how that is the case for industry, it gets even more interesting, because they require this rigor process so they can make better decisions based on the data that they have at hand. And the way that companies did that in the past was via a so-called data lake. And a data lake is a logical view of all the data sources that you have at hand, hopefully in their raw format, and available and accessible by data scientists to find new insights. So in the perfect world, we have an existing data lake. The data scientists have access to that, and then they can start working on that data. They don't have to worry about all the data gathering that we just talked about collecting it. It's all there already, and they can make their analyses. I can tell you though, even from my own experience and working with industrial companies, that many of them have in theory a data lake, But this comic over here shows it very nicely, because once you ask them, wait, let's have a look at that, it doesn't look really well structured on the surface. You have relational databases linking users to products, to location and prices. And once you look beneath that, you can see it's all done in Excel in terrible formats with terrible macros. And that's unfortunately the reality that we have to work with. And the issue here is not a technical one. I think it's more an organizational one, because no one really feels responsible for data unless they use it themselves. And that's why this idea of data lakes, data warehouses, is questionable and has been debated, especially in the recent past. And there is a solution for that called data mesh. And data mesh is a socio-technical concept that treats data as a product, typically using federated governance in the background and relying on domain-oriented decentralized data ownership, as well as a self-service data platform to enable data democratization. And in that last part, it's pretty similar to the data lake. But what I really want to stress here is that domain-oriented decentralized data ownership. That means once you start treating data as a product, it changes everything, because you also change the role of ownership. Earlier, you could have had a department which didn't really care about the data that they produced because they were not using it themselves or they were not interested in it. You would have this orders.xlsx file that I just showed you. But once you give them ownership and say, hey, the data that you're producing is your product in a decentralized manner, right? You're responsible for that. You have to own it. You have to make sure that it's in the right quality. And then from an internal thinking, you can provide this on a kind of marketplace, on a self-serve data platform where others can consume it and data scientists can work on that. That's a big shift in responsibility and in organizational setup. And via this federated governance, which gives you a federal policy on how you set up your data mesh system, but then you have these data products across different domains which can then be utilized. And this is characterized by these four main ideas of domain-oriented decentralized data ownership, right? So across the company, different departments or teams are responsible for the data in a decentralized way. You treat data as a product, not as some necessary evil, but as the core knowledge that you have within your company. You have a self-serve data platform where data scientists or AI engineers can work on, and this is all done by federated computational governance. And we try to show this granularity in this graph here. And what I want to tell you is that there's a shift happening from this traditional data lake, which didn't really work, or I've seen very rare examples where it worked, over to data mesh, where the ownership is decentralized with the domain experts, which is hopefully something that works way better. Okay, but let's assume you gather the data, either yourself through a rigor process. There's a data lake where you pulled the data, or there's even a data mesh concept where you internally bought the data product or received the data product from a different domain. The next step that you can do now with the data is sampling. And that is not necessarily something that you always need, but it's important to have that in the toolbox of data pre-processing. Because what it's about is, how do you identify the representative subsets that are interesting to the problem that you want to solve? Because it can be very inefficient to use all the gathered data that you have for machine learning. Simply computational, but also for you as a person to go through this and getting an understanding for the descriptive analysis, it might be important to pick a subset of that. So data collections can be intelligently reduced by sampling. What is sampling? That is defined as a selection of a representative subset from a larger amount of data. You might have heard that before. And there are different techniques that you can use to sample a potentially larger data set into a smaller one. First one is simple random sampling. So every data point in this larger data set has the same probability to get selected in the subset. There are rare cases where you want to do that, but again, it's entire randomness with the same probability for every data point. Then there's, of course, systematic sampling. So now all the data points are ordered according to some criteria that you have to define, again, keeping in mind the initial business problem that you try to solve. Again, depending on this problem, you might have a different systematic sampling because you will be interested in certain aspects of the data, whereas someone else solving a different problem might be interested in entirely different subsamples and thus might choose a different criteria. In one case could be the timestamp, in another case could be a certain treatment. So in this case, a start point is selected randomly and every data point in a specific distance, so every 10th data point, for example, is selected if you choose the timestamp as a criteria, and there you lose a little bit of detail, but you have a rather rough understanding. Then there's stratified sampling, so every data point is assigned to one of several categories that you have in mind. In time series, it could be months, but it could be also representative for a certain cluster of, I don't know, patients, for example. So in every of these categories, then you do simple random sampling again from the first one, because you say, I want to make sure that I have these clusters in my data set, so I'm going to pick a random point here. And then the final one is cluster sampling. Over here, you assign every data point to one of several clusters, again, based on a specific criteria. And then some of these clusters are selected randomly, and the joint selection then consists of the final subset. You could say kind of the most advanced one. And again, there's not necessarily a right or wrong. Again, I know a few cases where you would only do simple random sampling, but it depends on the problem that you're trying to solve. I want to give you an example over here. So let's say you have to do the sales forecasting for a supermarket chain. So precisely you want to predict the sales for specific product items in a nationwide supermarket chain. Now, let's say the data set is too huge for you to handle for the machine that you have at hand. So you have the sales data for whole Germany, and that's way too large. Now, what you could do is you could combine different sampling techniques. So first of all, you could partition the larger data set into several different sales regions, for example, based on the postal code. And then you could sample data from each of these sales regions and then potentially also train separate models on those, or have a larger model but made sure that you reduce those data points. And again, this is just an option that you have at hand. I just want you to be aware of it. Doesn't mean that you have to sample every time that you work with data. What you should do, however, and that's very important, is to look at the data distribution that you have in your data set. And that's part of this descriptive analysis that I talked about earlier. I know everyone wants to jump into building models, but the reality is that you will spend 90 to 95% on working with the data, massaging it, understanding it. And so these two steps of the descriptive analysis, of understanding the data quality that you have, E, and the data distribution that you have, D, is absolutely essential. And one of the key points is, if you defined your machine learning problem well based on the business problem, is what is the distribution of your different features, but most importantly, what is the distribution of your target variable? Why is that the case? Because it's key to know how your target is distributed, because later this will have implications for the choice of the algorithm and also for the metric. So that's like the first thing you should do when you get the data set. Let's say you sample it or not, and you did a little bit of pre-processing. You want to know what the distribution of your data set looks like. And there are different things at hand that you can use, right? You don't have to look at the bare numbers, but you can, of course, visualize that, right? So histograms, for example, use a pie chart, stuff like that, right? Anything that's helpful for you, for your human cognition and understanding, use these visualizations to have an understanding on how is your target variable distributed. Or in the case of regression, you can, of course, also plot it on a two-dimensional graph with the dependent variable on the one hand and the independent variable on the other. Of course, this is only two-dimensional, but it can help you in understanding the distribution of your numeric variable in consideration of one of the other features that you have. So that's typically the first thing that you would do. Understand the distribution of your target. And then typically there are two things that you might find out when looking at the distribution of your target or also on your other features, and those are sparsity and noise. And both sparsity and noise are very, very typical problems when it comes to the daily job of data engineers and data scientists. So first of all, what is sparsity? You can see a very nice depiction of that in the graph above, where there are simple cases, time spans where data is missing. So a sparse data set is a data set which contains mostly zeros, or doesn't contain any value at all, right? This NA is very typical that you will see in many, many data sets. And when you work with public data sets that are provided in university lectures or that you can find on typical pages like scikit-learn, they are well pre-processed and all the missing values are typically removed there or entered. But when you work with real cases, that is so typical that a bunch of data is missing because a sensor fell out, they use the different systems, and when you have these missing values, that is typically an issue because later on in the process, it will be harder for your algorithm to identify patterns in the data if there's just information missing, right? So again, plotting that for your target or for your feature will help you in understanding what is the data distribution look like. And by the way, that's also a data quality issue, right? Over here, it's summarized under data distribution, but of course, this is also an aspect of the data quality, its sparsity. And then the second case is noise, which is a random error of variance of a measured variable. So for example, if picking the case of sensors again, if you don't have digital but analog sensors, noise is very, very, very common, right? Whenever you work with analog data, which is then transformed into digital one, that's where you will see a lot of noise. So these are two very, very common issues that we have to deal with, and there are a bunch of things that you can do. But be aware of them, and again, very typical in working with real world data sets. I now want to give you an example why looking at the data distribution is so important, not necessarily with regard to sparsity and noise, but to how different classes are represented. And there's a really nice example from research, because in whole genome sequencing, which is a medical technique that is used to determine a DNA sequence, you have a representation of that very DNA as data points, right? Again, think of observations described by features, and in here we have the DNA sequence. Now, what you want to do is you want to build machine learning models that are used to find disease-associated genetic variation. So very rare types of blood cancer, for example. Now, as you can imagine, that's your target, right? You want to find, let's say, binary target. Does someone have that disease or not? So you will have millions or multiple millions of cases where the target will be no, right? This person does not have this rare blood cancer. This person does not have the rare blood cancer. And the positive examples, so the cases where you have this very, very rare disease, accumulate to several hundred instances. So that's what we call an imbalanced data set. Very, very tiny minority of cases where we can observe the phenomena that we're interested in, opposed to a large majority amount of observations where this phenomena does not occur. And that's a very typical case in supervised machine learning, because we're not interested in the majority, right? We're interested in these few positive examples. We want to identify those people who have this rare blood cancer. We want to identify faults in machines. When will this machine fail? The machine fails very, very rarely, but we are interested in identifying exactly these spots. So it's very typical to identify the minority case here. That's what we are building our models for. We want to know when the machine fails. We want to know when this rare cancer type appears. And that's a huge problem, these imbalanced data sets. That's a problem because the machine learning model will tend to ignore these minority cases, especially if you don't build them right. But I'm getting ahead of myself because we're going to look into the solution of that as part of the next lecture. For now, it's important that you plot the data distribution and see if there are errors of sparsity and noise, and especially if there's a high imbalance in your data set. Which brings me to the next point, the data quality. And again, to remind you, this goes hand in hand with the data distribution. Now, why does data quality matter? You could see the example of the students, and the only thing that your machine learning model can learn on is the data that you give it. So the better the quality of your data, the better your model can be in the end. And to put it in a negative manner, common saying in machine learning, you have to avoid this garbage in, garbage out scenario, right? The model can only work as well as the data that you give it. And again, you need to look at the quality of that data in relation to your initial business problem. One data set might be very well suited to solve one type of business problem, and in a different case, it might be terrible because especially those data that I'm interested in might be missing, right? So it's not necessarily easy to say this is a data set of high or low quality. It depends on the problem that you're trying to solve. And apart from the sparsity and noise, there are 6 criteria that can help you in determining what the data quality is for a given data set. First one is completeness. So the proportion of stored data against the potential of a fully complete data set. So did you cover everything, which I mentioned earlier? Were you rigor in acquiring the data, and does it cover the real world phenomena in its entirety? Yeah? Second one is uniqueness. Recall the student example. If we had the same student twice, the model could think that these were 2 different students, but could think that the pattern that you observe here in fact happened 2 times in the real world, when it was just a measurement error, because the table was joined and the student appeared twice in the final table that you gave the model. So uniqueness is very important. So you measure how many instances are duplicates, and of course then as a consequence remove these duplicates. Third, timeliness. So if you have great data, but that's 20 years ago, let's say political data on stock markets, and in the meanwhile we had Ukraine war, Brexit, COVID-19, then your data is not worth a lot for the problem that you have at hand. Fourth, validity. So is the data that you have, does it match a predefined syntax? So for example, if you take statements of customers, are these statements written in natural language, or is it just gibberish? Fifth, accuracy. So is the data correct or not, right? Is the information trustworthy that you have in there? And then 6, consistency. So if you look at multiple representations of similar instances, is it consistent across these instances? And the most typical issue here in the data quality is noise, which we already covered, mainly in the areas of both uniqueness and accuracy in my experience, but also in other researchers' experience. And I want to give you an example from my own research of data quality. So to not expand too much, but give you an idea on what I did my PhD on, I wanted to identify customer needs in social media data. Back then, the typical methods that you would be using for identifying customer needs, and not only identifying but also quantifying them, would have been to do surveys and do interviews in small focus groups. Obviously, this doesn't scale very well, when in fact we have people willingly expressing their needs on social media platforms like Twitter or X. So what I did is I wanted to find out in an automated manner, of course, by utilizing supervised machine learning, what are current needs in the field of electric vehicles, e-mobility. So I collected the data myself. I gathered it just like I showed you. So I wrote a Twitter bot which would collect any tweet containing any of these words over here, and then I would have a very large database of tweets containing that, and then I could train the model to learn where a need is embedded and where not, of course, by labeling that and having that as a target. And to give you an understanding on the amount of tweets I could work with. So for this period, which is 10 years ago now already, I collected around 110,000 tweets. So tweets where anyone across the world would use one of these words in his or her tweet. And after all the ads and spam and bot reduction, I was left with 7,000 tweets that I could work with. So 7,000 actually high quality tweets. And this gives you an understanding for the degree that we are talking about here. And I also want to give you another example from our research. And this one is potentially interesting when it comes to the importance of looking at data quality. We once did a study where we wanted to predict whether customers are happy for a large IT provider. And what we had at hand, which was very worthwhile for us, is a data set of IT incident tickets with the documentation of the IT problem described by the customer and some structured data as when was it created, what's the ID, priorities, stuff like that, right? So a ticketing tool, basically data from a ticketing tool of this IT service provider. And then the interesting spin to it is that we also had data of those incident tickets combined with customer satisfaction surveys, which were conducted after the completion of the incident process. So we knew for certain incident tickets, what was the customer satisfaction after that. So in supervised machine learning terms speaking, the customer satisfaction was our target, and all the rest was our features, our input, especially the additional structured data such as time, ID, priority, and so on. So we built a model to predict the customer satisfaction using the incident ticket data as input. And what we thought was of largest importance was to have the text of these tickets in there. Of course, you need to transform the text into a structured manner, but our expectation was, of course, the way that customers express themselves in these tickets will be vital to predicting the satisfaction of these customers. So model performance will improve across the board when we include the textual problem description, because people might be angry in those tickets and or very happy, I don't know, and that might help us. The result, however, was, and you can read it in the paper indicated here below. By the way, all of the papers that I reference, as long as I'm allowed to, I will upload them. The model performance did not improve, or to be honest, it even slightly decreased, because once you looked at the data, that's why it's so important to look at the data as a researcher and also get a feeling again for the data distribution, is it had nearly no emotions detected in the text. I have a few examples of these over here, right? You can see things like need assisting in migrating from version 4.5 to version 4.7 and so on. So very, very technical focus of the description. And what also comes into place here again, something that I mentioned earlier today. Typically, the models work very well if your N, so the amount of observations, is way higher than your P, the amount of features. But once you start introducing text, and I'll show that to you in a second how that works, once you start introducing text into your data, the data set will have a way larger feature space, so way larger P. And this typically also decreases the capability of your model. By the way, this is called the curse of dimensionality. So we had a very large amount of features compared to the data instances to the observations. And again, interesting case of data quality, right? You might assume, of course, I need to take the text of the ticket in here to predict the customer satisfaction, when it was the other way around, right? The structured data that we had at hand about the time they posted, the ID, the priority, helped us way better in identifying who of these customers was satisfied and who wasn't. Okay, and this brings us into the data pre-processing. So what methods do you have at hand to generate your own data set, to process data from potentially unstructured into structured data? And again, that's step we call the data engineering. And there are nowadays even roles for that called the data engineers. And to be honest, these two steps of data pre-processing and the feature engineering, so the feature engineering is the building of these features for a data set, they're very closely related. I try to distinguish between those two, but naturally they do occur together in reality. And I want to give you two examples on how we can work with unstructured data and transform it into structured ones so it's digestible by the algorithms. One of the main data sources, data types that are unstructured are images, and there are a bunch of things that you can and potentially need to do to clean these images before they're ready to be used in a machine learning model. So for example, sensor corrections, right? If you take a look at this picture over there, you have dead pixels there. So correcting for these geometric lens distortion, if you took photos, and vignetting are very typical. This also includes things like lightning corrections. This is stuff that people do when they work with Photoshop and work on the images afterwards. Also removing noise, for example, smoothing images, geometric corrections, rotating, flipping, changing the perspective, or potentially even color corrections. These are all things that you can do. And one way to, once you did all of these in the best case scenario, one way of transforming the unstructured image data into more structured one is you take every pixel, and every pixel becomes a feature, right? So with very high resolutions, that means you have quite, again, a lot of features because of dimensionality. Potentially your n higher than p is not fulfilled anymore, but that's one way of doing that. Once we get to the more advanced methods, there are also different ways, but that's definitely one way to do that. The other unstructured type of data is text. And there are different ways on how we can deal with text, because again, this is not machine digestible at first. So let's say we have this exemplary text called "This started as a text meeting all requirements." Now, how do I structure this unstructured text data? First thing that you do with this text is called tokenization. So that's a process of separating a string of text into its components of words. So we have these tokens afterwards. This started as a text meeting all requirements. Now all of these are all of these words from the previous text have become their own tokens. What you can also do now is, especially if you're interested in the grammar of these, is you can use part of speech tagging. So you identify the type of word by identifying its grammatical word class and then translating that. That could be potentially helpful for you. To counter the curse of dimensionality, you can do a pre-processing technique called stemming. So that's an algorithmic process of reducing the words to their stem, base, or root form. This does not necessarily result in real words, as you can see over here, but it will move certain semantically similar words into one of the same buckets, so features. So if you would have the word requires, required, requirement before, this would have been 3 distinct features. Now with doing stemming, this all becomes one feature called require. Again, no real word, but it might help you in reducing this curse of dimensionality. There's also lemmatizing, that looks up each word in dictionary and analyzes the part of speech and then selects the correct form in case of disambiguation, because one thing can mean can have multiple meanings, and part of speech can help you identify what are we talking about here. We'll get deeper into this as we move closer to the foundation models and precisely the large language models. But for now, you should have at least heard about these pre-processing techniques. There are a bunch of more things like substitution, so symbol, word, character removal, to have, again, unimportant features out of the picture, reduce the amount of features in general, right? So substitute emoticons, remove stop words, remove punctuation, things like that. You can also cluster words into so-called n-grams. So these are sets of co-occurring words. So in our previous text, that would be bigrams, for example, for the case of all requirements, it would be a bigram, or meeting all requirements would be a trigram. This could also help you to cluster. And then there are things like semantic pre-processing, where you identify so-called synsets, so synonym sets of groups that express the same concept on a semantic level. And there are even hierarchies in the synset called hypernyms, which depict superordinate relationships. Again, this is one way of approaching it. You have these options at hand, and there might be cases where you're more interested in these semantic meanings, and others where this is less the case. And to give you an example now on how we can pre-process it, again, I'm taking a tweet here, so we need more charging stations, and it has to happen soon. If we take this tweet and transform it into trainable numbers, we can do things like the username removal of the tweet, downcasing, tokenization, stemming, and stop word removal, and we can see how it changes its structure. Now we have the tokenized version, and now we will generate features based on that. So now every of these single tokens becomes one feature, and if a tweet contains that, we will have a simple so-called Boolean token presence or representation, which means you have a 0 if this word appeared in this tweet, and you have a 1 if it did appear in a tweet. And that's the process on how you transform unstructured text into a structured manner, so your algorithms can digest that. That kind of transformation is called back of words transformation. That is something that you should have heard. And this type of encoding that you can see here is called one-hot encoding. So the presence of a feature is simply coded either by a 0 or by a 1. And this has advantages and disadvantages, something that we can discuss in class. But that's one way of representing text in a structured manner. Now, next up are numbers. Two typical things that you can do when it comes to pre-processing numbers, and recall that numbers are already in the right format to be digested by your algorithm later. You just want to make sure that the quality is as high as possible, and that your model can identify the patterns as good as possible based on the data that you have at hand. And one thing that typically counters that are in numeric data, especially in time series, are outliers that you might recall from your statistics class. And one way to work against that is use smoothing, so that reduces the effect of outliers towards the bulk of the data points that you can see across the board. And what it does is it will weigh outliers with a lower weight compared to other more common data points. Of course, it's important that the outliers that you have are in fact outliers, and they do not have a semantic meaning. For example, it could be the failure of a machine, the one that you want to predict. So if you remove this by smoothing, you should be careful about this. But typically, this technique should remove noise and reveal the underlying data. The other thing that you can do is normalizing. So that is a technique that transforms the range of different attributes into one similar range. And there's a bunch of algorithms that will favor these attributes if you all have them normalized. To give you a few examples, on the one hand, for smoothing, let's say a dataset contains 10 data points. Now, every data point with 2 previous data points is not used with its original value, but with the mean of its own value and the value of its 2 predecessors. And if you would look at a graph of that, that would mean this smoothing method reduces automatically all the outliers that you have, and has a way more, in many cases linear, but in other cases a very smooth look in the visualization of that data. And the process that is being described here is called a simple moving average. And there are other ways on how to smooth the data. Again, depends on the use case, depends on the type of outliers that you have. Again, you want to make sure that in some cases, if there's an outlier that has a semantic meaning, it will keep that meaning and you will not smooth over it. Whereas, especially the example that I had earlier, when you transfer analog data into digital data, that might be a good case to actually smooth the data. And when we talk about normalizing, example over here is, let's say you have a data set that contains information about human characteristics, like their weight data from 50 to 100 kilograms and the length of their thumbs from 5 to 9 centimeters. One way that you could use is a min-max normalization. There are also other ways, just like in smoothing. We'll try out a few of these, by the way, as part of the exercise that we have. And this min-max normalization reduces both of these ranges of the weight and of the length of the thumbs to values between 0 and 1. And again, a bunch of algorithms will favor that type of range when being normalized. Again, very typical case of numeric data is time series data, and there are a bunch of things that you can do. We already talked about sparsity of data, and that's becoming especially important here when we talk about time series. And you have to deal with this sparse data, specifically with your method to replace these missing values, because otherwise your algorithm can't work on that. So what you could do here is you could use the value previous or after missing the one. You could use a mean, median, some kind of interpolation. So there are a bunch of things that you can do, but you need to replace the missing values with something. And then when it comes to other pre-processing step, you can choose, of course, different types of representation of the data. Again, by sampling, which we covered, by averaging, right? Doing linear interpolations, only use important points like minima and maxima, PCA, TSNE, and so on, which is more advanced. And you can include these as a feature, right? This goes directly into the feature engineering. So you could have a feature which only has maxima or only has minima, if it makes sense. Again, you need to talk to the domain experts if that is meaningful to do for the problem that you're trying to solve. And then, of course, you have a bunch of, finally, alignment methods, which are way more advanced methods. We had this case over here, which was a chemical process, and you wanted to identify cases where this process overcooked. That's what it was called. And you could always see this pattern over here at the very end, but it occurred at different times. So you have to use something called dynamic time warping in the end to match these two. But those are pretty advanced things. I don't think we'll get too deep into these, but just know that you have them at hand as a tool set. And that's the very process that I just described, is those batch runs in the chemical process. And what the dynamic time warping does is it looks for similar patterns of the time series and then matches these. So it can see that the end of the process always looks the same, and then before we come to this end, there's always a similar pattern over here. And this can also be performed in an online setting, so where you do this live, which was, for this very customer, quite important. Okay, now let's look finally at the feature engineering. So how do we build these features, these columns for our data set at hand, right? So this very step. Previously, our focus was on, we have somehow gathered data that was potentially unstructured, of low quality, etc., etc. We pre-processed it and now have the pre-processed data. And now from these pre-processed data, these X's, we now want to derive features that are meaningful. So features F to F1 to F16, right? Or however features you have. Again, P is the amount of features typically. And then, of course, have the target variable, and our machine learning model, just like in statistical learning, will distinguish between those as the dependent variable, our target variable, the one that we want to predict later, and our independent features, our input over here. And what you can do here is, now this is entirely in your hand, is you can, of course, use features to create new features. This can be either necessary because the format that you have at hand is not digestible by the algorithm, so like text, or because you know more about the certain domain here and think that the representation of a certain feature needs to be put different for the feature for your machine learning problem. And the feature engineering now makes use of a bunch of methods, many of them coming, of course, from pure mathematics and statistics. So let's say you have numeric data, the raw data. Of course, this can be now utilized by your machine learning algorithm without any further adaptations. But I mentioned that already. You can still do a bunch of stuff. And again, there's not necessarily a causal relationship between the steps that you perform and the performance of your final model, but these are possibilities that you can use, like calculating min, max, mean, median, variance, and so on. I talked about that. You could binarize the features, right? Reducing the feature to either 1 or 0. So for example, in all the cases where the frequency is not important, let's pick the example that we had earlier of the students, right? This was a binarization. All of them had a grade, but I just divided them into pass the exam or not. That is, in fact, binarization. If you have numeric values, you can also round them. Maybe it's not important to have the decimal points, and it's fine to work with the numeric integers. You can bin your features into smaller clusters with discrete feature characteristics, called bins, for example, with prefix range of bins or adaptive binning, depending on what you have. And you can do also, of course, things coming from the field of mathematics, like transformations, monotonic transformations, like log transformation or Box-Cox transformation. Again, you need to know when to use these and when they are meaningful, but this is a bunch of tools that you have at hand. However, you don't always work with numerical data, as we could see. So the other case is categorical data. We've seen that already with the text data after we transformed it into the tokens. So when you transform these categorical values into numeric labels, so your algorithm can digest them later, think about the logic behind these features. So you could either transform nominal attributes, so there's no sense of order amongst them, and then translate it into the numeric labels, or think about whether this could be an attribute which is ordinally scaled. So there is a sense of order amongst them, and then you need to consider that if you encode it as a numeric feature. And when it comes to this encoding, I already showed you the one hot encoding, which is performed for text data, as you could see. So does this single observation contain this word or token or not? And then it's either 0 or 1. Or it could do other things like dummy coding schemes, depending on also what your range of potential values is. And besides these manual feature engineering techniques, there are also automated feature methods. So there are principal component analyses, for example, that have a look at the correlation between the features that you have, and it will calculate a smaller set of so-called artificial features or principal components, that's where the name is from, that are linearly uncorrelated to each other. And PCA typically works very, very well in reducing your feature space. The only thing is that these principal components or automatically generated features do not necessarily have a semantic meaning to it. So when you show them to domain experts, you have to decompose them again into their original features to make any assumptions. And then there are, of course, things like automated feature engineering. And this is becoming more and more frequent and falls into a field called auto machine learning, short AutoML, or even auto artificial intelligence, auto AI, where you just basically throw over a data set over the fence, and then these automated methods will engineer features by themselves. And there are a bunch of things that can happen here. Okay, so let's come back to our overall initiation process, which we now went through, right? From the data gathering over to the sampling, to the descriptive analysis, and then to the data engineering. Because there's one more thing that I want to show you, or that you should have heard about at least, in the way that we think about the importance of data when it comes to AI. I hope one of the messages that I got across now is that the data is highly important. Your model can only be as good as the data that you give to it. And I think that has become clear, because however you design your features, however you however well you do your job in gathering the data and sampling it, this will ultimately determine how well your performance on the model will be later. However, this view needs to have a specific name to have this feeling for the importance of data. And this phenomena is called a data-centric artificial intelligence. And I need to expand on that a little bit. So in the past, especially in the research field, and by the way, for good reason, a lot of work was done on the models. So how can you build the best possible model for a given data set? You can see this tiny log over here, right? So the data set is logged, and then we try to systematically enhance the model to build the best possible model. So this so-called model-centric AI is the paradigm emphasizing that the choice of the suitable model type, the architecture, and the hyperparameters is essential for building effective and efficient AI-based systems. And that is definitely the case. But with everything that we learned today, I think we need to have a complementary view to that, and that is the data-centric artificial intelligence, which now says, let's not think too much about the model in the end, but think about how can we systematically enhance the data, how can we get better data sets in the end to then build better AI. And in reality, both of these views complement each other. Both of them are important, but again, the emphasis was too large on model-centric AI in the past, and I think we should move the discussion back way more to the data that is at hand, and see how we can enhance it. So we identified different ways on how you can do that, and you can see them over here in the data-centric paradigm, right? How can you systematically enhance data? And we pose a bunch of ideas here on how you can either refine it, so receive better data, or extend it, meaning you need more data. And of course, in reality, also both can happen at the same time, right? And it always asks about, do you want to improve the data quality on an instance level, so on the observational side, or on the improve the data quality on the data set level, right? On the features, basically. Or do you want to acquire new data? And again, I'm not going to read through all of these ideas that we have here that you can use, but I think it's important to keep that in mind. So to build the best possible data set that you can have, and actively think about how you can make it better, which could even mean acquiring new data for blind spots in your data set, and have this available in your tool set. So to give you two instances, what you can do is, again, we have this logic of observations or instances and features here again. There are things that you can do, right? So you can utilize synthetic data, for example, to extend your observations, right? You can improve the feature or target quality as part of the different requirements that we post. So for example, by utilizing imputations. Those are things that we talked about already, but I want to mention them again, right? How do I deal with missing values? Well, first you need to be aware of them, and then you need to adequately handle them. And then, of course, finally, you can change the volume of these features by engineering additional ones, just like we covered in this lecture. And that's for tabular data, but you have the very same idea, on the other hand, for image data, of course, where you can do a bunch of things that we talked about, right? So I want you to have this data-centric view when you think about AI, because I think it's really important, and people tend to forget about that because they're occupied with building the nice models and architectures, but data is really, really, really important. All right, so let me summarize. First of all, a well-defined problem statement with clear objectives and business criteria are key for a successful AI/machine learning application. I think you can understand that now. So understand the problem that you have. Talk to the domain experts. Get a good understanding for the problem that you're trying to solve. Second, there are different ways on how you can separate data based on criteria, structure, origin, and type. That's what we showed already. And then analyze that data, right? What does the data distribution look like? Do we have an imbalanced data? How should I bin the target variable? How should I work with that? And then finally, the steps that I showed you about data preprocessing and feature engineering help you in preparing potentially unstructured data into a structured manner, so your system can work as well as it can. All right, so now we have everything at hand that we need. We have a nice built data set, and then in the next lecture we can dive deeper into the models that we can now use that learn patterns in the data. So thank you very much for listening. Have a nice day and see you soon.